Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside. I am dealing out of the big ideas math sections of 9.1 to 9.3 on similar triangle aspects, starting with the Pythagorean theorem, then special right triangles, then similarity in right triangles, respectively, from Big Ideas Math Integrated Math 2 textbook. But I'm dealing in a worksheet that is not from them. It is actually from me. I didn't make the problems per se, but I generated questions of a sort. So I haven't tried the problems yet. Generated questions using certain software. I'll put a PDF down below if you want to check out this review. I think it was 16 questions. We'll go ahead and see how they are. They should go relatively fast. If you want to see more in the sections from 9.1 to 9.3, check out what I did in the IM2 playlist if you'd like to. And these will go in succession from 9.1 to 9.3. But like I said, it should go pretty quick. I don't even know if I need a calculator for these things or not. I think the numbers are small enough, but we'll go ahead and take a look. All right, find the missing side of each triangle. Leave your answers in simplest radical form. You have right triangles with two known sides and not the third side. This is where Pythagorean theorem is used. A squared plus b squared equals c squared. A and B are the lengths of the legs, and C is the length of the hypotenuse. The hypotenuse is always opposite the right angle. So don't mistake this slanted side as the hypotenuse. No, this is one of the legs, so is this, because they make the right angle here, and the hypotenuse would be x opposite it. So if I want to solve for x, I'm going to do 10 squared plus root 17 squared, and that equals x squared. 10 squared is 100. Root 17 squared is just 17, and that equals x squared, and x squared is 117. So x will be the square root of 117. Now, I don't know if that can simplify. I'm guessing if I generated the problem, I did that with the intent that it could. It can divide by 9. That's a certainty. It's 9 and 13? 9, I think so. So root 9 times root 13 reduces to 3 root 13. Now, these have units in the problems. I don't know if I intended on having those, but I'm going to go ahead and put meters. And that should be the simplest radical form answer if I did that right. And I'm sure I did. Okay, number 2, now this time x represents one of the legs. So when it comes to a squared plus b squared equals c squared, tomfoolery, x is either the a or the b. Let's just treat it like the a, and we get to say x squared plus your other leg is 13 equals root 197 squared. And this time 190, that's the hypotenuse. So we square that, we get 197. 13 squared is 169, and x squared still exists there. We subtract 169 from both sides to get x squared's value. That's 28. And take the square root of both sides. So now we get x is the square root of 28, which has a perfect square factor of 4. Square root of 4 is 2, and that gives you 2 root 7, and this is in miles. X is 2 root 7 miles. Again, I don't think I had any intent of having units on these things, but they are there, so when we answer them, we will do the same. Oh, I forgot to put this thing over here. I forgot I'm using that. So that was number 2. Excuse me. Okay, number 3. Or numbers 3, 4, and 5, and 6. Oh, I remember putting these in. This is still part of the same section. The following are Pythagorean triples. Find the missing side without using Pythagorean theorem. So you could. A squared plus b squared is c squared. The numbers will get relatively big. But here's the idea. We have some certain Pythagorean triples, and there is an infinite number of them. But the commonplace ones that we would know are the 3, 4, 5, Pythagorean triple, 5, 12, 13, 8, 15, 17, and 7, 24, 25. These are ratios of side lengths in right triangles that have all integers. And there are ones that are bigger, of which I don't know, but these are bigger ones. So how would we know these? Because in some way they are similar in triangles to these ones. How do we find that out? If we find the greatest common factor of the two values that we do have, then we can reduce it basically to its essence of what it would be in another state, to its similar triangle brethren. For example, I can divide this and this by 30. If you divide these by 30, then you get 4 and 5 meters, what have you, but this is equivalent to a blank 4-5 triangle, to a 3-4-5 triangle, if you made these 30 times smaller. Make them 30 times bigger again, right, and you get 120, 150. So that's the idea. This is all about triangle similarity, and you could set up a proportion, but the idea is make everything 30 times bigger. Times 30, times 30, and hey, times 30. What's x? X is 90. X is 90 meters. That will give you a 345 special Pythagorean triple triangle, right? That's what that is. Now, number 4 follows the same premise. Find the greatest common factor of 48 and 102. I want to say it's 8, but now I don't think it's 8 because, well, a couple reasons. That wouldn't give you a Pythagorean triple here, and 102 doesn't work there. How about 6? Divided by 6 is 8. Divided by 6 here is 17. So, yes, this would be the equivalent of, if I divide this by 6, an 8, 15, 17 triangle if everything's divided by 6. Times 6 is 48. Times 6 is 102. 15 times 6 is 90. 90 centimeters. Excuse me, for X. 8, 15, 17 triangle. And I'm checking these off because I believe I set you up with all 3 sets of them so you could practice them, work them out, and things like that. Number 5. Excuse me, the numbers are smaller. Sorry for that clipping there. You can divide it by 3, I think. That would give you, I think, the 5, 12, 13 version. 5, 12, 13. Dividing by 3. Let's make it 3 times bigger. 12 times 3 would be 36. So 36 yards there in the 5, 12, 13 special right triangle. And again, you can use Pythagorean theorem for these. It's just this is a more efficient practice. And they don't always appear as similar triangles. Sometimes they appear as these. I think probably more often than what I'm giving you. The point is, I'm saving myself time by recognizing this. Now, would I recognize this for myself if I didn't know I was in this section? I would for number 3. Maybe for number 5. When the numbers get bigger and more obscure like this, I'm like, I don't really know. But for the sake of this, it's really understanding what we're doing here, which ones exist, where we could hunt for them. And really, again, it's if I'm in these triangles. If I saw 5 and 12, I know immediately 13 is that third one. Anyway, let's look at number 6. X, the unknown, and we've got 144 and 150. Well, they're separated by 6. I'm imagining I can divide it by 6. And given that this is probably the last one that we have here, 150 divided by 6 is indeed 25. And this would be 24, if that's all told. So this must be the 7. 6 times smaller. Let's make it 6 times larger. X must be 42 feet. And that covers the 7, 24, 25 Pythagorean triple. So it's just, just throwing those into the mix. I don't think that's a really pertinent part of the review. In fact, if you use the Big Ideas Math textbook, they don't really have you use Pythagorean triples in a great way there. Instead, they have you do Pythagorean theorem and ask you if this thing is a Pythagorean triple, to which both of these answers are no, because these irrational values here or here or here would show you that they're not, whereas these ones are. All right, state if each triangle is acute, obtuse, or right. We're still in section 9.1, and this is the converse of the Pythagorean theorem. This time you don't know if you have a right triangle, but what you do is test it. Now, I was trying to decide whether or not I wanted to give you a visual of the triangle to make you know which one is representing what. You want the a squared plus b squared equals c squared set up to be so that the a and the b are the smaller values and c is the larger one. And you can imagine that root 177 is the larger one just because of the drawing. But could you do it without the drawing? Well, root 177, that's more than 10. 10 squared is 100, so, it's root 100. So clearly that's the longest side there as you set this thing up. So let's see. I don't know if it equals it or not. I literally don't know. I don't know if it equals it. Actually, I do now. It or not. So let's just kind of make a box and say, is it equal to, is it greater than, or is it less than? Because an acute triangle would have a squared plus b squared be greater than c squared. An obtuse triangle would have a squared plus b squared be less than c squared. And of course, we know a right triangle would have a squared plus b squared equals c squared. So let's see which one this is. 10 squared is 100, 9 squared is 81, and root 177 squared, of course, is 177. And please get down to the final simplified portion. Don't just assume. 181 is indeed not much, but greater than 177. If a squared plus b squared is more than c squared, then your triangle is acute. Not by much, but enough. No angle is 90 degrees. Or more. Number 8. Same test, same looking diagram. Do you know how big 6 root 2 is? Do you know if it's more or less than 7? Do you know if it's more or less than 11? How could we figure it out? We could square it. I mean, you could use a calculator. See, 6 root 2, I want to imagine this to start with. 6 root 2 squared is 36 times 2, that's 72. That's a part of what we're going to do anyway. I might as well set it up now. Now that I know it's less than 11 squared being 121, then I know where I sit here. I need to see, whoops, how these things compare. 72 plus 49. Well, that is 121. Excuse me. 121 equals 121. This is a right triangle. Right. This is a right triangle. It's not obtuse. The other one being acute was the less than, but this one's a right triangle there. I didn't know, and now I do. All right. Yeah, we're going to number 16. So the next four are for section 9.2, and the next four are section 9.3. I feel like the Pythagorean theorem stuff should be actually less emphasized. It's something we probably more know of, or not. I don't know. I think there are more different varying questions they could ask with that. So I did it. Let's see what we have here. Find the missing side lengths. Leave your answers as radicals in simplest form. My go-to for these things here is my 45, 45, 90 triangle has a 1 to root 2 ratio relationship of my sides. If either leg is 1, the other is the same. Whatever it is, the other is the same. And then the square root of 2, hypotenuse is root 2 times larger. In the 30, 60, 90 triangle, we have a 1 to 2 to root 3 relationship. 1 being the side opposite the smallest angle, 30, and 2 being the hypotenuse, actually, and root 3 being the long leg in comparison with this. Root 3 is actually less than 2. Make sure you know that when you're doing this. So I like to go from one of the legs to the hypotenuse in this one, and the short leg to either the hypotenuse or the long leg in this case. Find the missing side lengths. Leave your answers as radicals in simplest form. We start with a 45, 45, 90 triangle. Even though they only show you one, you'd have to know the others that. So y equals 7 is a for sure. Let's just go ahead and get that one out of the way. I'll even put it there. But y equals 7 is one of them. X, you got to take either 7 and multiply by the square root of 2. That's how many times larger this thing is here. What's 7 times the square root of 2? Yes, that's exactly what it is. No units involved in these problems. Number 10, we got to find the lengths of B and A. Now, this is the hypotenuse of this 30, 60, 90 triangle. Hypotenuse is twice as long as the short leg. I'd love to go and get B first. Don't assume to go alphabetically here. In order to get A, I'd love to get B first. Let's divide this guy by 2 because it's twice as long. So B equals 4 root 3 over 2, which is 2 root 3. Now that I know that B is 2 root 3, I actually want to use that to get A. Being root 3 times larger than that short leg, let's multiply that thing by root 3. A is 2 root 3 times the square root of 3. Root 3 times root 3 is 3, and 2 times 3 is 6. And that is A's value right there, 6. I didn't mark up number 10, I'm sorry. Boom, there it is. All right, number 11. We have another 30, 60, 90 triangle, as you see the 60 there. And we know the leg opposite the 60, the longer leg, which is root 3 times larger than the shorter leg. So we actually have to divide this thing by root 3. Now that becomes a little bit trickier. Y equals 4 divided by root 3. In some cases, a valid answer. It's in radical form, but not simplest radical form. Here we want to rationalize the denominator. We're going to multiply the top and bottom here by the square root of 3 as to not change its value, but to change its appearance, get the denominator to be a rational value. You get 4 root 3 over 3. We've been fortunate in the past for things I've actually done with my students to make this clean up. 4 divided by 3 would, or whatever. But that doesn't clean up here. That's the simplest version of the answer. You can disagree all you want, but that is, in fact, simplified. And that is why. That's why. X is just twice as big, so we just got to multiply that by 2. X is 4 root 3 over 3 times 2, and then just take the 4 times 2, and you get 8. 8 root 3 over 3. Not necessarily a rewarding answer set, right? We like to see something that would really make it feel like, yeah, we cleaned things up. Not really, but it still works out. Now, B and A in this 45, 45, 90 triangle are congruent to each other, so whatever one is, the other is. I'll just say A equals B equals, what is it? And here the hypotenuse is root 2 times larger than either of them, so we are going to divide by root 2. So we get 4 root 5 over root 2, and we run into the same issue as before. We must rationalize the denominator. Nothing I can clean up here with even the 5 over 2, so let's just multiply top and bottom by root 2. And I'll get 4 root 10. See, this time this part multiplies. That guy there, over 2. 4 over 2 is 2, and you get 2 root 10. Make sure that the root 10 itself isn't something that can simplify. It's not. There's no perfect square factor inside of it. So each of those are going to be written as 2 root 10. And that's the essence of your 45, 45, 90 triangle, 30, 60, 90 triangle workload that you can use here. Special right triangles have their place in unit circle trigonometry. So even though you won't necessarily use them in IM2, you'll use them in IM3 and pre-calc and calculus and all that stuff. They are very, very, very commonplace. Not like in every problem, but anytime that you're using something of the sort, it's huge. And without a calculator. Trigonometry, though, is coming up for this chapter, 9.4 to 9.6. So get ready on this channel. Okay. Find the missing length indicated. Leave your answer in simplest radical form. We are now talking about right triangle similarity. This is section 9.3. There is more than a way to go about these problems. I will go about it in the textbook way that is mentioned, and I'll go about it in a way that I would probably more favorably talk about setting up proportions based on the actual similar right triangles themselves. There's something called geometric mean, which allows us to set something up in a certain way. There's this whole x squared equals a times b thing that goes on based on how a and b are set up in a certain way. And when you have this hypotenuse broken up in certain ways, your variable can be solved, or these legs can be solved in a certain way. Again, I bring this up, I say all this very unconvincingly because I'm not really a fan of this memorization formula stuff. I'm not. But I'm going to go ahead and set it up for you anyway. This guy, when you square this guy here, x squared equals this length times this length. Oh yeah. That's not something I'll actually remember. Next year, I won't remember it. A times B, if you will. Now I'm going to change what these are. B is 64. Probably shouldn't have written those in the first place. B is 64, and A, well, we didn't find out this length yet, but because this part's 55, 64 minus 55 is 9. So I can turn the A into a 9. There you go. So there is my other guy. X squared is 9 times 64. Yeah. So let's go and solve for X. We're going to take the square root of both sides there. And, I'm actually going to do 9 times 64. I'm just going to leave it be. Take the square root of 9 and get 3, square root of 64 and get 8, and X is 24. Now, it's relatively fast if you know the formula. I will get to this aspect of the formula in now a different light, the one that it might sound longer to you. You might be like, well, that's dumb. Why should I use that? Well, because you might remember it better. Or not. I don't know. But triangle similarity is enforced. I know that X has to be involved. How can I identify X? There are 3 triangles. There's a small triangle, to which X is the hypotenuse. There's a medium triangle, to which X is not related. And there's a big triangle, to which X represents the short leg. Represent X in one of the 2 ways. Short leg or hypotenuse. Short leg of big, hypotenuse of small. Let's say short leg of big. Short leg of the big triangle. Actually, let's say hypotenuse of small to begin with. Hypotenuse of the small triangle is here. Do we have the hypotenuse in any of the other triangles? Not in the medium. Here's the hypotenuse. We don't have that. But in the big triangle, we do have the hypotenuse. It's 64. So hypotenuse of small is to hypotenuse of big, as I need something else small to big that corresponds. I know, see, here's the medium triangle. It has 55 in the long leg, but we're not doing long leg. We're not using the medium triangle. But in the big triangle, we have the short leg. So short leg of big, can we get the short leg of small for this? Yes, it was 9, right? So hypotenuse of small over hypotenuse of big equals short leg of small over short leg of big. So we cross multiply. X squared equals 9 times 64. That's where you get to there. Set up the proportion, and that's where you get. Okay. So that's the concept that I'm going to drive with. So I'll do both. I'll do both as I set all these things up. We already solved that, though. Number 14. This is the only case where I do know my geometric mean a lot better. I feel better about it. This and this, X is the geometric mean of these 2 lengths here. So this 16, 20, 36 minus 20 is going to be used here. So this X squared equals, this is going to be 20 times 16 is going to be the setup. Let's do our square root business again. Again, I can just take the square roots of these things kind of more in an individualistic way. Square root of 20 is 2 root 5, and the square root of 16 is 4. And 2 times 4 is 8. So X is going to be 8 root 5. Once again, no units here. So we're just going to leave it as that. That's a final answer. As far as a proportion of this thing goes, again, involve X. There are two triangles in play for which I should be considering most, because x is involved in the small triangle and the medium triangle. As you may know, because x is the geometric mean of these two values, x is in between these two values. It's somewhere greater than 16 but less than 20. Therefore, x represents the long leg of the small triangle, but the short leg of the big triangle, of the medium triangle. So I can do long leg of small over long leg of medium, that's 20, equals short leg of small, 16, over short leg of medium. That would be x again. There's my thing. When you cross multiply, you get to this x squared equals 20 times 16 scenario. And then you solve. Okay, number 15. This time I'm more enthused to actually give it the other way. Let's actually set up the proportion first so it doesn't look like, oh, look, it just so happened to be. Let's involve x again. X is only one thing here. It's the long leg, of the medium triangle. Now, in case you are considering using 4 plus x here as the hypotenuse, that's a plus, as the hypotenuse of the big triangle, note that there's nothing else that you have in the big triangle. I keep wanting to write 4x. Note that you have nothing else in the big triangle. You don't have the short leg or the long leg, and you don't have the hypotenuse of the medium or the small triangle, so I don't think there's any value in that. But x does represent the long leg of the medium triangle. Do we have a long leg of another triangle? Yes, the small triangle. We have the long leg is 4 root 3. Now, we got to go medium to small triangle again. In the medium triangle, I also have the short leg, and in the and then I have the short leg of the small. So perfect. Long leg of the medium to long leg of the small, short leg of the medium, short leg of the small. When you cross multiply here, you're going to get 4 root 3 will be squared this time, and you get x times 4, or 4x. This harkens back to what we were doing. You don't automatically say x squared equals 4 times 4 root 3, right? That's not what this thing was. 4x is not automatically the geometric mean of what you do. X is just a variable to be solved for. This altitude is the geometric mean of these two numbers here. So once again, it's kind of why I wanted to set it up a different way and show you that. So this is our setup. We're going to square 4 root 3. 4 squared is 16. Root 3 squared is 3. And that's 48. And divide by 4, you get x equals 12. So again, even if you knew the formula, even if you understood what you were supposed to do with it, some people would just automatically square x, think that they're doing right by themselves, and they're not. And the last problem here, the last problem for this review, we will do this stuff one more time. Once again, dealing with the altitude bits. Now, this is once again, so I'll set up proportion, I'll talk about it, and actually it harkens back right to what I said about number 15. If I wanted to say x, I'll go, hey, x is the hypotenuse of the big triangle over, let's find a hypotenuse in another triangle. You actually could. 16 and 4 root 33 are the legs of the small triangle. I could use Pythagorean theorem and find this third side, find the hypotenuse of it, and I would have something that corresponds. I actually am enthused to try that with y'all. As long as I have things that correspond in the big triangle, which I would then, and the short side. So I might actually consider that. But for now, with the items given, for easier calculations, it's not there yet. So I couldn't use x right now because I have nothing else in the big triangle and I have no other hypotenuses. But I actually want to go do that afterward. Just give me a sec. So how do I use x? Well, you have to see what else you do have, I guess. It looks like I could maybe write 16 minus x, and then I have the long leg of the medium, which can then apply to what we had here. Short leg of small, long leg of small, short leg of medium, long leg of medium. And we have the same thing now here, and we can do that same essence. So I can use 16 minus x. The long leg of the medium is to, say, the long leg of the small, 4 root 33, as the short leg of the medium, 4 root 33. Once again, geometric mean of these is to the short leg of the small, 16. And you would have to do the same thing if you use the other formula. You would have to do the same thing if you use the other formula, or do the other thing I mentioned, the Pythagorean theorem bit, which I still want to do. Cross multiply here, now I get 16 times the quantity 16 minus x equals 4 root 33 squared, as both of those multiply with each other. That's 256 minus 16x. Excuse me, I may have to use a calculator here. 16 times 33 is over here. I can divide everything by 16, actually. That would actually make things easier. I probably will. Let's divide everything by 16. And you get 16 minus x equals 1 times 33, so 33. Add x to both sides, subtract 30. Is that a negative number? I guess so. It's going to be a longer value. Oh. Let me make sure I did everything right. But add x, subtract 33. I get x is negative 17. The reason why I'm not certain about that is because this is a length right here. And that wouldn't seem to agree with what... Oh, it's not 16 minus x. It's x minus 16. Hold on a second. That's the problem. X minus 16. Now, it's not going to change very much stuff. I have to erase some parts, but it's not going to change the overall construct of what I get. Very, very sorry about that. Let's kind of change that again. So this is x minus 16 here. X minus 16 and 16x minus 256. I divided by 16 anyway, and I get x minus 16 again. There we go. So plus 16 to both sides. Let's keep that. Add 16 to both sides. You get x equals 49. Now, I want to be certain that all that's correct, so I will do it one more time now that I'm padding the runtime of this. I will do this one more time, not even with that geometric mean version. I'm just mean in that way. I'm just going to do it this way. Let's do it again, but this time let's try and find out that hypotenuse. Let's find out what this is here. Let's just call it a c. Let's say a squared plus b squared equals c squared, like that. 256 plus, I never found out what 16 times 33 was. 480, 48, 528. And I don't know what 256 plus 528 is. 784. Oh, I think that is... Is that 28 squared? Let me check. 784 square root. Yep, 28. So C is 28. All right, that's a fun number. So, okay, I'm going to turn this number to 28. Now, why does that help me? Now I can use just x, not x minus 16, because x is the hypotenuse of the big triangle. I can say the hypotenuse of the big over, this is the hypotenuse of the small now, 28, equals the, what else? Now I have to go big to small. Short leg of the big, 28, over the short leg of the small, 16. And I get 16x equals, back to 784. Let's see what happens when you divide 784 by 16. Do we get 49? 784 divided by 16, 49. So x equals 49, which, by the way, is, once I found that out, then I would do the whole 28 squared equals 16 times x, which is literally what we just had there. So that does give us our answer, and that's it. Sorry for the mishap on the x minus 16 versus the 16 minus x. I don't know why I made that mistake. That was a rookie mistake for myself. But guys, that'll do it for this one. This is a pretty quick thing overall. This is Mr. Robinson. Thanks so much for watching. Sorry for Big Head Steve Kerr in the background. And I will do the textbook review for the Big Ideas Math 9.1 to 9.3 quiz portion coming up next after this. So thank you. Take care. I will see you in the next one.